All right, everybody, welcome to week 4. The response I didn't get about the Canvas quizzes and the auto grader and everybody worried about partial credit. I got those this weekend instead of last weekend. So you're a week later getting me those than I usually see them. Reminder, don't worry if you immediately get shown that you have a 0 out of 10 on the quizzes, because the way that the auto grader works here, I'll pull up the way that I to show how this works. This might help you understand what's going on in some other classes. So when I have to put in the right answers for these quizzes, so the way that this works is when I have to do something like this question, I go to edit it, I type it in there. The way that it has for these fill in the blank ones, the numerical answers, the numerical grader on Canvas just really doesn't work very well, and it doesn't support using units or doing sig figs well. So the way that I've settled on doing this is basically we're just gonna do fill in the blank questions. I'm grading the number and the units and the sig figs just like normal. I just can't use the automatic grader function from Canvas to do numerical answers because it doesn't do those things. So the way that I have to write in the possible answer is I literally just type it in. If you change even one character to what you answer, like if you forget to put a space between the 2 and the kilogram, where I frequently don't put spaces between my numbers and my units, it'll register as 100% wrong when you got it 100% right. Even if you just add a space to the end, you can't even see it, and you're gonna get marked down and have no idea why. That's why I go back through and regrade these all by hand, so don't panic about those. Right, there's not a way that I can actually input all the possible ways that you could write the right answer. Because I'm not gonna sit there and put in 72 different versions of the same thing, right? So the right answer is gonna be there. If you get marked down but you have the right answer, don't panic. I don't want you to be worried about that. It's just the limitations of Canvas quizzes create this situation. Questions about that? Robin?
On the first quiz, it didn't let me type in any kind of
Right.
units, so I sent you the noise, I left out the units because I thought.
Yeah, so for this one, I'm not gonna take off points for units because last week's didn't let you do units, but from here on forward, when you get a question like these, writing the whole answer, including the units, and including the right sig figs.
Thank you.
Yeah. Any other questions about formatting or grading on the quizzes? I did see a few while we have this open. A few of you asked about getting a digital version of the conversion sheet in case you lose your paper one. Those ones, go all the way to the bottom. There's a resources button at the bottom. And these two things, the equation sheet and the periodic table, this is going to be exactly the way that I'm going to give it to you on the test. So if you want to practice, if you want to print out your own periodic table, your own conversion sheet, these are the ones I highly recommend using because that's what you'll be having on the test. So in the vein of you want to practice how you're going to perform in a game, you want to practice using the same tools you're going to have available to you when you take the exam. I would highly recommend using it. This is just a PDF version of the same one that I handed out in class on Wednesday of last week. So if you saw that one, you don't need it, but if you want a fresh copy, rather have it on a computer rather than on a piece of paper, that's where it is. There's other random stuff here, other versions of the periodic table. We'll talk about the periodic table starting this week, as well as some other things that will become more useful as we get closer. You don't know what Vesper geometries are yet, so that's not all that relevant. Same with polyatomic ions. We'll get there, and then some of these other handouts will make more sense. All right, let me put questions up. We're gonna go through, also a lot of you wanted to go through number 3 on the quiz. So we'll go through that. We'll go through all three questions. It shouldn't take us that long. That'll be our conversion practice. For today, we'll just be working through the quiz problems here in a minute. Several questions about types of chemistry. Somebody asked about, is there more physics in chemistry than chemistry in physics? Well, kind of, because all chemistry is applied physics. Chemistry is just physics without the assumed resistance equal zero stuff that physics does. Chemistry is physics in the real world, just at a really small scale. So you really can't separate physics from chemistry. Just like you can't really separate biology from chemistry either. Biology is biology because of all the chemistry that's going on inside the cells, right? So that's one of those reasons that chemistry is considered the central science, is because if you understand chemistry, you can go in either direction, more on the physics side, more on the bio side, and still kind of have the background necessary to understand what's going on. Along with that, different types of chemistry, like inorganic versus organic versus physical versus analytical. Physical chemistry is really just getting at that interface between physics and chemistry. So it is sort of the root of all chemistry is physical chemistry. When you take physical chemistry you are a chemistry major, you might take physical chemistry. It's usually a 3rd or 4th year class, and usually there's the quantum version and the classical version. You have to take both. We'll get into some of the basics of the quantum side of things on Wednesday. But the other side of it, of physical chemistry, is stuff like designing engines. So mechanical engineers actually have to take classes that are really similar to physical chemistry in a lot of ways, because that's how you do the math for figuring out how efficient an internal combustion engine can be, or how much energy is stored in batteries and things like that comes from the physical chemistry side of things. Organic chemistry does not mean that they didn't use pesticides. Organic chemistry just means it's carbon-based. Anything that's focused on carbon-based chemistry is considered organic chemistry, because in the 1800s, they actually didn't understand that you could make biological chemicals in a lab without living systems. So they called it organic chemistry because they thought, oh, these chemicals only come from living systems. And it wasn't until somebody was trying to do inorganic chemistry, which is basically everything that's not carbon-based, and he accidentally made urea in the lab. He was trying to make a new way of making its molecule called thiocyanate, and he accidentally made urea, which had previously only been known to exist in living systems. So that was sort of the birth of organic chemistry, and sort of where kind of laid the foundation of biochemistry after that. Analytical is just how do we get more sig figs on things? What do you have and how much of it do you have? There's actually an entire field you can go into based on how do I figure out what this is and how do I get more sig figs on it? Which sounds really boring until you realize that there's a governing body for that entire field. So you can actually get a job where your job is actually maintaining lists of conversion sheets, things like that, deciding who gets to put how many sig figs on the official periodic table. Or it's a organization called NIST, which is National Institutes of Standards and Technology. They're the ones who decide what a gallon is, what a second is, what the official time for the United States is. There's an entire lab organization dedicated just to that. So you can kind of go a lot of, the way I keep saying things, that every topic we're going to touch in this class is its own upper division course if you're a chemistry major. And most of those are there in an entire field of study that you could spend your entire career on. If you keep zooming in, and this is just going to be a real broad overview of a lot of those topics. Everybody always wants to know about explosives. What's the most explosive chemical compound? Well, it kind of depends on your definition. Everything's a chemical compound. So if we want to say what's the biggest explosion that you can have, then we're talking about thermonuclear bombs, which is chemistry, fusion bombs. If you want to talk about more, what's the most explosive thing we're going to do in labs, that's probably when I take the metallic potassium and throw it in water. It pops, gives you like these white purple flames. It kind of looks like a firework if I get a good enough chunk in there at just the right momentum. It's lighter than water, it's less dense than water, so it floats. And so if I throw it into the water, it flies back up and kind of looks like a firework a little bit. That's what happened to the ceiling in the new lab. Why are humans obsessed with gold? It's shiny. It's relatively rare, it's easy to work with, and you can find it in nature in its metallic state. So it made a really ideal currency, because there's really only 3 metals that you find in their metallic state. It's gold and silver, and then sometimes copper. Iron mines don't really find metallic iron, they find iron ore, which then has to get processed and turned into iron. So gold has always been around because it's shiny. You can find it in the ground sometimes. That's exciting if you're a prehistoric human. Then last but not least, current events thing. Trees exploding when it gets really, really cold. They don't explode like explosive compounds explode. It's basically just when you get lots of water in, or they have these trees with really thin bark. So they oftentimes, when it gets really cold, the trees will actually basically break apart because the cell walls burst when you freeze things. Like sticking celery into the freezer, when you pull it out, it becomes really like soft and soggy, right? That's because of when you break apart those cell walls, those plant cells wind up losing a lot of their rigidity. If you do that when there's already a whole bunch of weight on the top of a tree, like an ice storm, then you basically have a whole bunch of force around, and then there's a really weak area where they've got some water in it, and then it froze and burst some of those cells. So they're also called frost cracks, more appropriately. They can be a couple feet long, and they make a really big noise, but it's not like there's like shards of wood flying in forests in Minnesota in the winter. It's more like if you walk around and it's really quiet, you might hear some popping. If it's a really cold day, but it's not like the trees are falling on people or anything like that. You don't really have to take cover when it gets cold out because of the exploding trees. All right, relevant quiz questions. We're going to do some practice with this. How do you find the first conversion? How do you know where to start? Basically, it's kind of like doing a jigsaw puzzle. It's impossible to say what the right first piece is, because depending on the way your brain works and what you see and the patterns you've started to recognize, you don't have to start looking and work forward. You can start at the ends and work inward, just like finding the edge pieces to a jigsaw puzzle. But there's a little bit of room in there for wiggling around. It takes a little bit of practice, which is why we're going to keep practicing with it. Grams per cubic centimeter it's usually what we use for chemistry. The kilograms per cubic meter is used a lot in engineering and economics, but that's really hard to measure. If you visualize a cubic meter of something, like that's a lot. It's like half of a truck bed filled with something. If we're not going to fill a truck bed with liquid mercury, so if we're doing conversion with liquid mercury, grams per cubic centimeter usually makes more sense. Exact versus rounded conversions. Are the conversions going to get harder, or are they going to go away? Neither. Conversions aren't going to get harder. If you can get good at conversions, we're going to use that as a problem-solving tool in a lot of spots. That question 3 on the quiz, the whole point of that was to try and see how you can use conversions that you didn't even know existed as a way to problem solve. And same with using speeds, and percentages, and densities. So we're going to keep going with that, because we're going to eventually turn it into what's called stoichiometry, which is a way of saying, so we're going to talk about chemical reactions in more detail. But if we started with a really basic chemical reaction like burning methane. Methane is natural gas. If you burn methane, presence of oxygen, you get CO2 and water. Every combustion reaction gives you the same products. Except that do the conservation of mass, we actually have to balance this to say, okay, it's one methane molecule reacts with two oxygens for this reaction to happen. When you do that, you make two water molecules. So we're gonna start talking about conversions in the sense of, okay, well, every time I burn one methane molecule, I make two waters. That's a conversion in and of itself. Right, because we can say for every one molecule CH4, I make two molecules of H2O. Which is gonna be, basically we can use conversions to predict how much of a product we can make. And it's really, this is the chemistry application, but if you replace all of this with just food items, like instead of methane, if we said, okay, I'm gonna take one ostrich egg and I'm gonna make two omelets with it. That's a conversion too. For every one ostrich egg, I can make two omelets. I'm just trying to make the numbers work with something that I could come up with off the top. For every one bicycle that reacts, you can get two wheels. Like that's a conversion too. And when we get used to thinking in terms of conversions like this, that's a really powerful tool. So the conversions aren't going anywhere. We're just gonna keep adding more ways that we can use them. And then last but not least, before we start actually working through these problems, I realized it's been a really long time since I first learned how to multiply fractions. And that's one of those things that when I learned it back when I was in 6th grade, it made sense to me, so I never really thought about it that much before. And putting it into a calculator is actually, if it's been a while since you've done math, putting it into a calculator can be actually kind of tricky, right? So when we're working through these problems, I'm gonna actually write it out the way that I would type it as well. I'm gonna show the work as the fractions like we've been doing, and then we'll actually enter it in properly. But basically, if it's on the top half of the fraction, you multiply by it. If it's on the bottom half, you divide by it. So when I say something like 10 miles into feet, 1 mile is 5,280 feet, right? I know I'm going to take 10 and multiply by 5,280 because the 5280 is on top of the fraction. If it was on the bottom of the fraction, I'd be dividing by it. You can also just type it in to your calculator times 5,280 over 1. When you type that in, if you just wanted to type it out long ways for every single one of your conversion factors, that won't steer you wrong. It's just a lot of extra typing on your calculator. So instead you can just say 10 times 5280. That just saves you some time, that's all. Okay, but more practice with that as we get going. I guess I never addressed the sig figs. Since we have this open, last one, and then we'll start working on these. The equation sheet tells you which conversions are exact and which ones are approximate. All conversions within the same system are exact, meaning infinite sig figs. When I say in the same system, I mean it's imperial to imperial or metric to metric. Any conversions between systems are approximate unless otherwise noted, because there's a few of them, like that one, that are exact. And since it's not clear, since we use the same units for time, I just specified that all of the time ones were exact other than 1 year to days. Right, so within the same unit, exact. Or within the same system, they're exact. Within going between systems, approximate, unless you're going centimeters to inches. Right, and for the most part, like our when we talk about temperature, These are exact, I specifically marked off this 273.15 is measured. But you're gonna start getting more experience with this and figuring out, being able to tell which ones are exact or not, as we get more experience. So let's do the conversion. If you already did these and you're happy with your answers, then just hang out and bask in your own success. Otherwise, if you want more practice, you can start from a fresh sheet of paper and redo it. It's not the most exciting thing if you already did these yesterday, but more practice is never a bad thing. You talk to the people around you too. If you got hung up on number 3, ask the people around you real quick. I'm gonna give you a few minutes. Talk this through. It's okay to struggle, as long as you keep struggling. Yeah, no, this was want to try to take generally speaking, campus is actually a better option. It's preferred, but since I have this in my info.
Yeah.
It's okay, I did get your email, but don't worry.
Yeah. Very good. No, the last one I actually tried, I think. Never like that, I didn't. Oh, no.
I think beginning and I go. Including I respect.
Yeah. Oh, yeah. Okay, sorry, I was like. You know, sorry. Yeah, so that's good. This one's 30.
All right, so working through this first one. You're given a density. And if you look at your units on the density, that's kind of a clue what we're gonna do. Your density is grams per cubic centimeter. Question is, how many kilograms are in a brick of gold that has these dimensions? So you're given dimensions and length. A density, which is our way of converting from a volume to a mass. So we need to take those measurements and get a volume. Because once we can get a volume, we could just use that density to go from volume into grams. Right, so figuring out what type of units you're in and you're trying to get to can kind of tell you what you need to do to get there, right? As soon as you realize, oh, I can get a volume here and I'm trying to get to mass, there's your clue. I need to be using density to do it. Because the density is your only real conversion that goes from volume to mass. And so once we get that volume, 10 times 10 times 40. Watch your sig figs, because we have 3 sig figs, 3 sig figs, 3 sig figs. So our volume can only have 3 sig figs, and so we can't just write 4,000. It is 4,000 cubic centimeters, but if we write it like this, that's an ambiguous number, right? We don't like ambiguous numbers. We want to write it out very explicitly how many sig figs we have. So the best way to do that is to just use scientific notation, especially if it's a big number where you're gonna have zeros that don't count at the end. That's not a sig fig. We don't want to count that one. So to make sure that we get the right number of sig figs, scientific notation. If you watch your units, we had centimeters times centimeters times centimeters. And remember, our rules for what we do with units are just like they are with variables. If this was 10x times 10x times 40x, that would wind up being x cubed, right? The units behave just like variables that way. So we're in cubic centimeters. Our density is in cubic centimeters. So cubic centimeters, we're going to put cubic centimeters on the bottom so that it cancels out. So we're going to be multiplying by 19.3. Then we have grams, we want to get to kilograms. So if we're trying to get to kilograms and we're in grams, that's a mass to mass conversion. That's just a metric prefix one. So check your conversion sheet if you don't know that one off the top of your head yet. The kilo means 1,000. So 1,000 grams is 1 kilogram. Thousands on the bottom, so that means we're going to be dividing by 1,000. So I'm plugging this into my calculator. Calculators don't understand sig figs, right? So when I'm typing this into my calculator, I might not go to the trouble of writing that all out, scientific notation. As long as I know that that's 4,000 and it's only 3 sig figs, you can type it into your calculator as just 4,000. And then we're gonna times 19.3 because it's on top, divided by 1,000 on bottom. And so this is what I would enter into my calculator with the way I would actually type it out. If you wanted to type it out the full way using scientific notation, you can use that 4.00 e to the 3 times 19.3 over 1,000 or over 10 to the third. We talked about this shorthand, right? This is our shortcut for writing out scientific notation. It's that capital E. Right, so 4E3, E is short for times 10 to the. Right, so if I'm trying to put in scientific notation, that's the key that I would use. Most online calculators also know what that means as well. So if you go to just Google search bar and typed it in just like this, it should give you the right answer. I have to hedge on that because every search engine starting to shoehorn in more and more AI stuff. And AI does not necessarily know how to do this properly. So don't take the AI overview. You want the actual calculator function from Google if you're using that search engine. Or get a calculator on your phone. Or get a EI-83 or something like that if you have one that you can borrow. Those are still kind of the gold standard for being able to type stuff in relatively quickly without having too many bells and whistles. There are also, who's bought a TI-83 recently? Like in history, does anybody remember what it costs these days? If I'm remembering right, they're still like $80, right? They were $80 when I was in high school. That's not market manipulation. I don't know what is. Anyway, All right, so questions on this first one? Do our steps make sense? Ish? As long as I'm the one up here with the pen? That's standard at this point. We've got another density one. What's the density in pounds per gallon? This is a density that's reported in grams per milliliter, not grams per cubic centimeter. I just said that grams per cubic centimeter was kind of the standard. For whatever reason, we know that milliliter is the same as a cubic centimeter. If it's a liquid, they tend to write milliliter instead of cubic centimeters, even though it's the exact same unit. But so I'll tend to slip up and do that as well. Time. What's the density in pounds per gallon? Here's a fun bit of trivia, maybe not trivia, as it's actually relevant to you. I'm currently grading the final exams for the class that I'm finishing up at the high school. It's also Chem 100, and their final exam had this exact problem on it in the conversion section. So questions like this are going to come back. It was even liquid mercury, if I remember it correctly. So if we're trying to get that grams per milliliter into pounds per gallon, what's the easiest way to do that? Do we have a conversion for pounds to grams? So we could just say 13.7 grams. We can check our conversion sheet and see that 453.59 grams is 1 pound. It's on the bottom, so we're dividing by it. And then we also, can we convert milliliters into gallons? It's not going to be as clean, but we have conversions to do that, right? We've done that a couple of times now. So 1 milliliter. I tend to mix up that conversion. If I'm going from mental memory, I tend to mix up the decimals on that quarts to liters conversion. I just know it's really close to 1, so I'm not going to use that one. That's totally valid. If you wanted to use to go from milliliters to liters, liters to quarts, quarts to gallons. I just don't have that one memorized as well. So I'm going to go the long way because I do have those ones memorized. So I can say 1 milliliter is 1 cubic centimeter. I'm going to write that in, even though mathematically that doesn't change anything, right? We're multiplying by 1 over 1. But then I can say, okay, well, 2.54 centimeters is 1 inch. We got to do that 3 times because it's centimeters squared, or sorry, centimeters cubed. So we're going to cube that whole conversion. This is where you want to be careful. If you originally got taught how to do conversions by just doing, I don't know what they call it, but when you set it up just like this, like it's like a number line where you fill in the top and bottom. Mathematically, that's just a simplified way of writing it like this, right? To make you think you're not dealing with fractions because fractions are scary. The problem with that is that people forget to put that there because it doesn't look like a fraction. It doesn't look like parentheses. I like the parentheses because it makes it really clear where to put that exponent and what's happening mathematically. That's helpful to some people, but it's not actually a mathematical step, so I don't like that way as much. I'm not going to mark you down if you're going to write it that way. You just got to be careful, especially when you're doing stuff with like these cubes. Just an observation. Once we're in inches cubed, our other conversion besides 4 quarts is a gallon is 231 cubic inches is 1 gallon. Right, so there's 1 times 1 divided by 2.54 cubed divided by 231. So it should be a pretty small number. When we do this. And then we're gonna take those numbers and we're gonna just do the division. Right, because we're gonna get our number in pounds, we're gonna get a number of gallons to pounds divided by gallons, that's our density in new units. I think it winds up being something like 115. Ish. Then again, like I said, I've been correcting this problem all weekend, but I think I used different sig figs for it. So it might not be 115 for us.
114.
114? Pounds over gallons. We're not gonna keep all of those sig figs though. We've got 3 sig figs here, so our answer can only have 3 sig figs. Not so bad. I glanced over as many of the questions as I could before class today, and it seemed like most people were able to do number 1. People started to struggle with number 2, and then everybody asked about number 3. Yeah.
I'm getting saying 140.19. And I did it like, I think I was wrong in the.
Okay, let's calculate this out so we can get the individual numbers here.
No idea where I'm going now.
So 13.7 over 453.59. Get 0.0302. And our number down here. It's probably when you're cubing that 2.54. So 1 times 1 divided by 1, so that one doesn't do anything. So I'm typing this in as 1 over 2.54 caret 3. Then I'm gonna take that number, divide by 231. And I get 2.64 times 10 to the minus 4.
Yes, it's.
So one of the things you have to be careful with these exponents is it's pretty easy when you're writing it out to wind up with something like 1 over 2.54. If you just do caret 3 over 231. Your calculator is not going to necessarily, it should, if it's following PEMDAS, it should do that 2.54 to the third before it does any of the rest of this, right? Exponents comes before multiplication in PEMDAS. However, some calculators will interpret this to mean that. So when you're doing when you run into an issue like that.
I do them all separate in separate chunks, so that doesn't.
Okay, so what is 2.54 to the third?
$16.387.
So then enter it in like that, don't do the exponent first. So when you do this, you should still get 0.000264.
Yeah.
So when in doubt with his exponents, do the exponents separately before you plug it into your calculator. Your calculator should all be able to do it properly, but sometimes they imply parentheses where there aren't any, or you might be putting parentheses in a way that's unexpected that kind of makes it act weird. So when in doubt, break it into separate calculations. So now when you do it,
No, I still get the 0.000264 number, so I don't know where I'm going wrong.
So then we're gonna take this 3.0302 and divide by the number in gallons. So 0.0302 over 0.000264. And I get 114.39.
I was forgetting the zero in front of the Thank you.
No problem, that's a really common thing to do. If you hear me say you slipped a decimal point somewhere, usually that's what happened. You left off a zero here, or you forgot a zero at the end somewhere. So if you get the right digits, but off by a factor of 10, that's probably what happened. Right, it's really easy to slip a decimal place when we're dealing with all of these prefixes and things like that. All right, let's do the tricky one. It's not that bad. You've got a speed. It's just in weird units. Still just a speed, right? It's not even really that weird units, it's just really, really large numbers. 16.9 kilometers per second is as fast as it sounds. So we have a time. 48.38 years. We have a speed. And we want to know how far did something go given us a starting amount of time. So we're going to go through time units. We're going to then use the speed to get to distance. So all the other steps, this is our general logic. We're in time units. If you want to go from time to a distance, you need a speed. So then everything else about this problem is just getting my time units. I'm starting with time in years. If I'm going to use this speed as a conversion, I need to get to time in seconds. And then that'll get me a distance in kilometers. I want my distance in AU, which is a unit you've probably never heard of, but it doesn't really matter. All you need to know is it's a distance and it's equal to this many meters. So if I'm writing out my plan in a little bit more detail now, this is definitely one where it can be helpful to start at the ends and work inward. I know I'm trying to get to AU, right? I only have one conversion for AU. So that means I need to get to meters, because once I get to meters, I can go to AU. Well, how do I get to meters? I get to meters from kilometers because my speed is in kilometers. So how did I get to kilometers? What's the unit before kilometers? Seconds. Right, so this is the step where we're using the speed. And then if I'm trying to get to seconds, there's only one other number in here really. We have 48.38 years. So if we're trying to go from years to seconds to kilometers to AU. So this is a conversion that we've done before. We've gone from years to seconds. This is a conversion, we haven't done it before because we've never used AU, but it's still just distance conversions, right? The only real tricky spot here is that we have to use the speed to go from our time to distance. Just like up here when we went from, used a density to go from a volume to a mass. And so this is our completed roadmap. Now all we have to do is find the right conversions that fit in for each of these arrows. So every one of these arrows is a conversion factor. So 48.38 years. 1 year, 365.24 days. 1 day is 24 hours. 1 hour is 3,600 seconds. Now we're in seconds. It's convenient at this point because you got to the end of your piece of paper, stop and hit equals there. I have a little bit more room, so I'll go one more step. We're talking about a spacecraft that has a set speed, an average speed. For every 1 second, it travels 16.9 kilometers. We started in time, we went through a bunch of time conversions, now we're in distance, in kilometers. It's gonna be a really big number. All right, if I'm doing my reasonableness check before I hit enter on this. If I'm just doing mental math here, I'm just gonna call that 50. Because that's close enough to 50 for doing math in my head. 50 times 300. Well, 50 times 100 would be 5,000, right? Times another 3, so we're at 15,000. I'm just gonna call that 10 for the purposes of doing this. 15,000, now I'm at 150,000, times another 1,000 there. So I was at 15,000, now I'm at 15 million, times another factor of 10. So I should get something in the tens of millions range when I hit enter here. Maybe off by a factor of 10, maybe in the hundreds of millions, in the low hundreds of millions. What do we get when we plug this in?
0.58.
10 to the 10?
Yeah.
I did slip some decimals in there, huh? Oh. Yeah, I was off by a couple factors of 10. So even though I did my reasonableness check and this number doesn't match what I expected in my head. That's just cause to say, okay, well, wait, did I make a mistake or did it, when I thought about it in my head, or did I make a mistake when I punched it into the calculator? It's just a reason to go back and double check. Now we have a number in kilometers. We just want to get that to AU now. We're almost there. And so 2.5. Well, let's talk about sig figs though first. Should we have more sig figs than 2.5? Yeah, we started with 4 sig figs. That's a measured number. But it's got more sig figs, so we're not worried about it. That's exact, that's exact. That's a measured number. So is 2.5 something?
It's 2.58.
2.58. Sorry, you probably said that and I just didn't hear. 2.58. 10 to the 10. Kilometers. Go back to your roadmap. We're trying to get to AU, which means we've got to go through meters. Because our only conversion for AU is from meters. Luckily, kilometers to meters is one we know how to do. 1,000 meters is equal to 1 kilometer. And then we can say 1.4960 times 10 to the 10, 10 to the 11 meters is 1 AU. Turns out space is really, really big. Even small distances in space, like the distance between the sun and the earth, is still really, really far by our standards. You get something like 100. So, and just also for context, so Voyager 1 has traveled 172 AU since it left Earth 50 years ago. It only in the last, I want to say it was like 5 years ago, could you make the argument that it finally left our solar system? So our solar system is something like 150 AU from the sun to the edge of the solar system. It's only 1 AU from the sun to Earth. So when you see drawings of all the planets and the sun in the middle, you know, mobiles, if you were actually doing those to scale, they'd be absurdly far apart. For context, who's had Bruce as a teacher here? He teaches math and physics. Anybody had him yet? One of his big hobbies is he goes geocaching, which is basically like grown-up treasure hunting. Where you go and you like hide something in the woods somewhere and you leave clues for people to go back and find it. It's kind of a weird niche hobby. Pretty cool though. Bruce built a scale model of the solar system, where the Capitol Dome in Carson City is the sun. So something about the size of this room in Carson City is the sun. Pluto is right over there about 200 yards. Space is really, really big. All right. Questions about the quiz? Yeah.
I forgot, did you say how big the sun was, at the dome, like the scale?
He made it so that the dome itself would be the sun.
Okay, that's.
So if you picture the sun, or sorry, picture the Capitol building in Carson City. The top of the Capitol building is the sun, and then he spread everything else out between here and there. It's really, really big. It was really cool when I was at University of Colorado, their planetarium has a big dome. And they did the same thing where they made a scale model on their campus where the planetarium was the sun, and then they put little plaques around campus. I only remember because I had to walk by Neptune on my way to work every morning. All right, logistics questions, calculator questions. All right, let's talk about some conceptual stuff. We're gonna do a thought experiment. So this goes back, I want to say about 4,000 years. Goes back to Aristotle. Aristotle and this guy Democritus they both graduated from the academy in ancient Greece at roughly the same time. They lived in different cities in ancient Greece, and they had an ongoing sort of feud. They did not like each other for whatever reason. Why they didn't like each other is mostly lost in history. We probably never know. But it was bad enough that when Democritus died in a whole different city in Greece, Aristotle traveled to his home city and then went to the library in Democritus's house and had all of his writings burned. Because Aristotle just straight up didn't like the guy for some reason. And part of it was that they argued, but that's kind of how they did things in ancient Greece. They didn't actually do science in ancient Greece the way we know it, because they didn't actually like form a hypothesis, test a hypothesis, adjust. They basically just logicked their way through things. They used philosophy rather than science at that point. So this debate started because this is what happens when we start dividing a piece of copper wire. They knew about copper at that point. It was soft enough that you could take a pair of shears and you could actually cut it. So they would take a piece of copper and they would cut it in half. And then they would take that and they would cut it in half again. And then in half again. Eventually you get to the point where the shears can't cut the copper wire anymore. Pretty quickly you get a piece of copper that's too small to actually be cut with shears, right? What this thought experiment was well, okay, well, what if we had really, really good shears? What if we kept going? Would we ever reach a point where we couldn't cut the copper in half anymore? And so just from logic point of view, there's only two options. You can either go till you can't cut the copper anymore, or you can go until the copper gets infinitely small. So again, they didn't know science, scientific method, but they had some idea of some of the underlying math. So the concept of infinity was something that they understood. Aristotle was of the opinion that matter can be infinitely small. And you just get different types of matter by mixing together varying amounts of the four classic elements: fire, water, air. What did I miss? Earth. Thank you. If you mix those together in different proportions, that gives you every type of matter on the planet. And Democritus basically said, no, there's no way. There's some point where you can't actually cut it anymore. Where you get to the point where you're basically left with small indivisible particles that he called atoms. And his most famous quote that still exists is, nothing exists but atoms and empty space, all else is opinion. It's basically like everything that exists is just matter. One of the first documented materialists in the Western thought traditions. But they're not really doing science. And Aristotle lived longer, and his name was Aristotle, and he was already famous for being, see if I get the order right, Socrates' student was Plato, whose student was Aristotle. So he's already famous because he's Aristotle and he studied under Plato, and he lived longer than Democritus. So basically this idea disappeared for a couple thousand years. And it wasn't until the late 1600s, early 1700s, that in what's called the Enlightenment in Europe, where basically some of these rich white dudes who didn't have anything better to do found some of Democritus's old writings. And by this point, they had discovered the scientific method. And so they said, well, we can find a way that we can test this. And so what we call atomic theory had a huge, 3,000, 4,000 year lag between when it was first put forward by Democritus and when it was actually science. And really, you can't fault Aristotle because they in theory both had equally plausible reasoning for this, and they didn't have a way to test it. So Aristotle was just going with what he thought made more sense based on the philosophy. So these three are the ones that kind of laid the groundwork for modern chemistry. So the first historical use of the word chemist to mean something other than just like alchemy. Alchemy was where chemistry has its roots, but that was basically in the Dark Ages. You had somebody at the court of the noble or of a king who could mix stuff together, make bright colored flames and flashes and things like that. Maybe they could make some potions that do, in theory, cure the bile humors in your body and, adjust things and leach you and things like that. That's where chemistry has its roots, is in alchemy. But it wasn't until, I want to say this was 1500s, a Scottish scientist named Robert Boyle, wrote a book which I'm trying to spell the old English way because it's cool. The Skeptical Chemist. The Skeptical Chemist was basically taking Francis Bacon's ideas of the scientific method and applying it to alchemy. So that was late 1500s. 1600s, these guys come along And they find Democritus's old writings and like, let's find a way that we can test this, let's see what we can do. And so Lavoisier was one of the first ones who came up with the conservation of mass. Because it seems like if we go back before the scientific method, if you burn something, it's gone, right? Well, Lavoisier was the first one to say, well, it shouldn't really disappear. If we burn something, but we collect all of the gas that comes off of it when we burn it, it should weigh the same as it did before. So he's one who basically, in the conservation of mass, most of you are probably familiar with the idea, mass is neither created nor destroyed. You can change what form it's in, but you can't actually change the mass of something. And then Proust, not the same Proust who's a famous author in literature, different Proust, same time though, came up with what he called the law of definite proportions, which was basically you always had the same recipes. Things always combined in the same ratios to give known products. So for instance, if you combine hydrogen gas and oxygen gas, it always takes these 2 grams of hydrogen. Hydrogen, I can spell. Plus 16 grams of oxygen. Always gives you 18 grams of water. So if you have extra hydrogen, it doesn't matter, it will always combine in the same ratio. And they wouldn't have known anything like H2O, so I'm going to write it the way. So regardless of how much oxygen or how much hydrogen you have, it always combined in the same ratio. 2 grams hydrogen to 16 grams oxygen. Okay, so now we just have textbooks full of different like ratios of things in terms of their mass. It wasn't until Dalton who then realized that you can actually make different stuff from the same ingredients if you change the ratio. Dalton figured out that if you take 2 grams of hydrogen plus 8 grams of oxygen, you make hydrogen peroxide instead of water. So what Dalton really realized, where he made his great leap that changed everything about science in Western history, was he realized that the difference in these numbers is always a whole number ratio. In order to go from the hydrogen peroxide recipe to the water recipe, you had to double the amount of oxygen. You never saw recipes different recipes from the same components that didn't have a whole number ratio between the ingredients. And so that's what he called the law of multiple proportions. And from that, and from these other 2 things, he made this big leap to say, oh, Democritus was right. If we consider these not just by their mass, but as discrete objects, and every one of those objects has a different weight, then you get atomic theory. All right, what's the difference between a theory and a law? Who remembers?
Law explains what, here explains the why.
Exactly. Law says what, theory says why. Here are the laws. The theory takes all 3 of those laws and says this is why those 3 laws exist. Why they happen the way they do is because all matter is comprised of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from other elements. Those atoms can combine in simple whole number ratios to form compounds. And his last piece was atoms cannot change from one element to another, they can only change how they are bound to other atoms. So back in the 1700s, this was huge. Now with our knowledge of modern science, I don't expect that everybody knows all of modern science, but most of you probably can spot at least one place where this falls apart. Corbin?
Quarks and
Quarks, we know that there are smaller pieces. We also know you can actually change atoms from one type to another. Although it takes a lot of energy to do so. That's what radioactive process, radioactivity in nuclear reactions is the change of one element to another element. But that's sort of the fringe case. That's the not the standard rule. So basically this worked pretty well as a theory to explain things. And then what happens with science when you get more information, you amend the existing theory and laws. Right? And so just to reiterate, laws are not immune to that. Just because it's a law doesn't mean it never changes. Right? When Einstein came up with his theory of relativity, that changed Newton's laws of gravitation. Very, very small amount, so that by the standards of the time, they couldn't really measure that. We've since gone back and been able to say, oh, now we definitively know that Einstein's corrections to Newton's laws are real. It's a real thing. That's how GPS works. We didn't have Einstein's relativity corrections, GPS satellites wouldn't work. Because the GPS satellites are moving fast enough relative to the surface of the Earth that we have to take relativity into consideration, or else we get the wrong answers when we try to pinpoint where things are. So these might need to be amended. Like, they're not really indestructible. It's not, all atoms don't have the same mass. They have, basically, we need to get better at defining what an atom is, what an element is. We'll see why some of these other ones come apart, but this is the big one. Simple whole number ratios. Compounds are made by taking elements, by taking atoms of specific elements and putting them together in the same ratio. And it has to be whole numbers. You can't have a part of an atom. Going back to this slide. It's not that we can't divide the copper anymore. If you get to a single atom of copper, understanding how nuclear reactions works, we can actually say, okay, well, we actually can divide that copper atom. But when we do so, it's not copper anymore. So there's basically a smallest unit that if you break that apart, it's no longer the element you started with.
is that because the subparticles are identical across elements, or is it just an arbitrary definition?
Yes, this is because the pieces that make up, so hold that thought.
Okay.
Is we're an hour in, now would be a good time to take a break. Let's come back at 11:35 and we'll finish up.
Well, like, it's not the same, yeah, seriously.
That's what I'm here, you take this one.
So that's like, I like the conversation or something like, no, that mark zero. Okay.
Thank you, Sasha.
My dentist. Right, it makes. I actually was. I'm kind of thinking. No, I'm just so bored that I wrote. That's why.
How'd you wind up getting the best classroom?
You know, I don't mind this classroom other than that pillar, but I do like the smart board it records things pretty well. Some of the other classrooms, hey, you have to use the webcam and use the whiteboard, and it's a little bit, doesn't translate quite as well, but
It's like the lighting.
it's not in the, you'll be glad that you have in this class in the winter, cause in the spring, it gets real warm sitting right there.
Feels good at first.
Yeah. The other big classroom is directly across the way over there. It used to have window air conditioning units in it, which did help with the heat. But the problem is that the snow would slough off the roof and hit the air conditioning units periodically, and it would sound like the roof was falling down. It was good for keeping people awake, but not so good for staying on topic and. All right. So let's recap real quick. Dalton came up with this idea, atomic theory. So this is sometimes called Dalton's atomic theory because this is the version that he specifically came up with. What this basically did was it allowed us to say, okay, all these different elements that are just atoms, everything we can make is just putting them together. If you like building Legos, not that they had Legos at the time, but if you can picture, okay, I've got, at the time there was they probably knew of 50 elements or so at the time. And if you say, okay, well, I have 50 different Lego pieces and everything in existence is just made up of those 50 Lego pieces combined in different whole number ratios. And so Legos is a pretty good analogy because you don't use half of the Lego ever, right? You're using a Lego, you pick the Lego that has a specific shape and you put it together. You bind them in the right ratios, you get much larger structures. And so it wasn't until this that they could actually do things like write 2 hydrogen plus oxygen reacts to make H2O. The idea of a water molecule that's made up of 3 smaller pieces was totally foreign until Dalton's atomic theory. And so you never saw things written like this because they wouldn't have known what you're trying to convey. They would just say, well, water is 2 grams of hydrogen for every 16 grams of oxygen. But they didn't know what Dalton added was that those 2 grams of water were 2 hydrogen atoms and 1 oxygen atom. And I say grams, they're really much smaller than that. We'll talk about how we count atoms in a little bit. But the reason that law of definite proportions existed was because we were combining them in these whole number ratios. And so then they started compiling like lists of recipes basically. Say, okay, well, this molecule has this ratio. This element has this mass associated with it. Every 1 atom of nitrogen has this many atomic mass units. And they started putting them into tables, and so they could say, okay, nitrogen has a mass of 14.01 AMU, where AMU stands for atomic mass unit. And that atomic mass unit is basically exceptionally small. We have a conversion for it that comes from one of the other big scientists at the time that we'll talk a lot about him specifically when we talk about gases, was a guy named Avogadro. Not avocado, Avogadro. And Avogadro basically came up with a definition for this AMU. He said, well, hydrogen's the smallest element we have. You get a single hydrogen element by itself, let's call that 1 atomic mass unit. And everything is built off of that. So they had this way of measuring AMU. They had these tables. And typically the tables were just like you see. They didn't look anything like the periodic table yet. It was just like an index at the back of a textbook. And it would have just said something like nitrogen, symbol N, 14.01 AMU. And they probably, for the most part, they just listed them either chronologically, like when were these different elements discovered, or they would list them alphabetically. And bear in mind, this is before you even had typewriters. This is when, in the age of the printing press. So to reorder the way that you wrote these elements was a non-trivial issue. You basically had to print a whole nother textbook if you wanted a table that had them in a different order. And I don't know if any of you have ever looked into how a printing press works. It's basically like wood stamps that you had to align in just the right order to spell something out. Then you would roll ink on them, and then you would press all of those stamps at once into a piece of paper. So it made it so that you could make the same thing a whole bunch of times in a row pretty easily. But if you wanted to change anything, you had to take all of those wood blocks out and reorder them completely. So it was incredibly tedious. Not like we have now where you can copy and paste things from one document to another, sort by this, anything like that. That didn't exist. You couldn't even just retype it. You actually had to reset it. Do that, which is actually where the word reset comes from. A reset means to start from scratch, basically, right? So in printing press days, that would be taking your big tray of wood blocks, dumping it out, and starting over. Setting the wood blocks by hand again. So Mendeleev is one of the most important figures in chemistry. Yeah, he definitely designed one of the most iconic pieces of chemistry. Mendeleev basically, what he contributed is he realized that if you changed that order, if you listed the elements by size instead of chronologically, and instead of alphabetically, that there was a pattern that showed up. So he probably was not the first person to list these elements by size, but he was the first person that when he listed them by size, he noticed that every 8 elements, you had some repetitive properties start to show up. Hydrogen is different than fluorine, but it reacts in a similar way to fluorine. Fluorine reacts in a similar way to chlorine. Helium reacts in a similar way to neon, which reacts in a similar way to argon. And all of these similarities happened when they were 8 elements apart. So then lithium did the same thing with sodium, beryllium did the same thing with magnesium, etc. Right, so Mendeleev's big contribution was he said, okay, well, what if I put all of these elements that have the same properties into columns? So I'm basically gonna, when I get to neon, I'm gonna take this and put it underneath over here. And then I'm gonna take the, another set of 8 elements starting at potassium and put them underneath over here. So Mendeleev invented the periodic table as we know it was because he looked at this list and said every 8 elements something repetitive happens. And so one of the simplest, or something similar to what he would have been working with, starts looking like this. This shape, they didn't know why. So this is another one of those examples of law versus theory. The law that he was noticing is also called the law of periodicity, which is just every 8 elements or every set number of elements apart, you get repetitive properties. They didn't have a why for that yet. Mendeleev is an interesting dude. He was the youngest of either, we don't actually have great records because he was Russian, born in the early 1800s. He was the youngest of either 13 or 17 kids, we don't know which. But he was the youngest of a really big family. His father was a university professor of Russian literature in the early 1800s. But his father went blind when he was in his early childhood. And it wasn't like there was like a whole lot of disability access or anything like that in Russia in the early 1800s. So what do you do when your literature professor goes blind and can't read anymore? kick him to the curb. So Mendeleev grew up having started in this middle upper class family in Russia. Then they lost all of their income. His mom took a job working in a factory that her uncle owned to try and get by. And then the factory burned down. So then she said, okay, well, all of my kids are out of the house other than Dmitry here. And Dmitry seems like he's really doing very well in his schooling. So I'm going to move across all of Russia to a new city where I don't know anybody, but they have the best university. They didn't call them universities in Russia at the time. I think they called them gymnasiums. But basically when he was at 13 or so, he entered into university and excelled. But by all accounts, he was not a very pleasant person. Which, you know, growing up with a childhood like you're in a Tolstoy novel can have that effect on people. But I like to use this as an illustration of just how much people didn't like him. So he designed this. This is one of the earliest copies of a periodic table. And he found gaps in it. He said, well, there should be something right here. We don't know what it is though. So then people would go out and start looking for it, for something that had those properties that he predicted, and they would find stuff. So he's directly responsible for finding these three elements specifically, scandium, gallium, and germanium. And germanium specifically was the one that he like staked his reputation on. There is an element there, even though you can't see it yet. When they finally found it, you'll notice it's named germanium. And I said Mendeleev was Russian, right? I don't know how many of you know your 1800s European history, but for most of their existence, Germany and Russia have not gotten along well. It was named germanium. The speculation is that as a direct screw you to Mendeleev. They named it after his country's greatest rival because they didn't like him. This is the guy who invented the periodic table. And he doesn't even get an element named after him until Mendelevium, which was discovered about 100 years after he died. Basically, Mendeleev didn't get an element named after him until not only had he died, but everybody who had ever known him died. Because if you knew him personally, you apparently felt strongly enough that you would have blocked him getting a name on an element. He just was the sort apparently to burn bridges. Which I always find fascinating when we get to know the scientists a little bit as people. Not the person in science history that I would choose to sit down and have dinner with. Like, might be a fascinating conversation, but it would not be pleasant. All right, so why do we have these properties? So what Mendeleev didn't realize he was doing is that by ranking these, by ordering them, putting them in these groups, it turns out it was the number of electrons that they had that was actually governing those periodic properties. And so, okay, timeline wise, Mendeleev was born in the early 1800s, discovered the periodic table invented the periodic table in the 1860s or so. And pretty soon after that, we had some other things getting discovered, kind of simultaneously. So it turns out they had these atoms. Like, okay, we have atomic theory. Oh, we needed all these different recipes to make all these different compounds. But what they figured out is that if you take a vacuum tube, which is just a tube of glass where they've used pumps to pull all the air out of it. You seal a vacuum tube with two pieces of metal on either side and you apply a voltage to it, you can actually generate what they call cathode rays. They behaved kind of like light did. They traveled in straight lines, but they could measure and see that they had a negative charge. They could measure the mass. They found that they were about 2,000 times smaller than hydrogen. But I already mentioned that hydrogen is the smallest atom. That's why it was chosen to be 1 AMU. And they also figured out that no matter what material you used, you could make the same particles. So they called them cathode rays, even though they were particles. because they moved in a straight line and they were so small, they thought they couldn't really be matter. They couldn't actually be particles because they were so small. So what actually is this then? What did they actually measure? It's not hydrogen, it's 2,000 times smaller than hydrogen. Even if you don't know what it is, what does this information tell us about atoms? You asked about a relevant question, Corbin, right before break.
Yeah, for sure. I was just asking if these subparticles of atoms are identical across elements, or if it's arbitrary that they say, oh, they can no longer call it that element.
Right, so that was a bit of an anachronism, which means that you use some information that was out of time. You used the word subatomic particles. They didn't know what subatomic particles were, right? Because as far as they knew, an atom was as small as you could get, and hydrogen was the smallest possible atom. So the fact that they could find something smaller than a hydrogen tells you that subatomic particles exist. There's something smaller than atoms. And the fact that they were all the same, no matter what material you put on each side, you got the same properties. So basically what they took this to mean was that all of our atoms have smaller building blocks that you put together. And so what Mendeleev really discovered was that these tiny cathode rays, which the scientists who discovered them named them electrons. If you have an atom and you can pull these electrons from it that have this negative charge, and all of these electrons are identical, means that all of our matter is made up of these smaller pieces. Even though we have this whole table of the atoms, of the element types, there's some level of organization smaller than that. Right, so let's take this further. We know that atoms are neutral. They don't have a charge to them. But the electrons, those little tiny particles, are negative. So what else do we know about the rest of the atom then? What does neutral mean in the context of a charge?
Something positive.
There's got to be something, if we have a negative charge on the electron, but the atoms are neutral, there has to be something positive canceling those charges out.
How were they able to do that experiment using electricity? Did they think electricity was atomic?
They didn't have any idea what electricity was. They didn't realize that electricity was made up of electrons. All they knew at that point, this was about 150 years after Volta in Italy first built a battery. So they could build a battery. They knew that if you take two different metals and you connect them with a wire, that you could actually get something to happen. You could get it to react, and you could even then use it to power something like a light bulb. But they didn't know what was doing that. So this is also the era where you see lots of terms like aether. Aether was basically thought to be like this invisible substance that light traveled through, the way that sound waves travel through air, or that physical waves travel through water. Aether was this invisible substance that light traveled through. So there was a lot of like speculation, like, okay, well, is it a wave? Is it a particle? Is there some medium, some dimension we're not capable of understanding yet that's allowing these things to happen? So they weren't really able until this to put together what a battery actually was, what electricity actually was. So back to the original question, if the electrons are negative, the atoms are neutral, there's got to be some neutral means that the charges add up to zero. So there's got to be something positive. Right, so this led to what's called the plum pudding model. Not a great theory. It turns out it has its reasons, which kind of makes sense when you think about if this is all we know. It's not a bad way of thinking about it. You've got these electrons sort of embedded into the atoms. And if you push on them with enough voltage, you can basically get the electrons to fly out of this stuff. And that's what they found in these cathode ray tubes. So the guy who first did this experiment, I think I believe that was Thomson. And he was also Scottish. He's the one who came up with the plum pudding model, I think. I might be missing a generation. It was definitely his lab. So in research in the sciences, you kind of have like your academic genealogy, which is like, okay, within this group, we produced these scientists who went on to produce those scientists and teach other scientists. It was definitely in Thomson's research group, came up with this idea of the plum pudding model. And it also kind of makes sense. They called it a plum pudding model because they were from the UK, and plum pudding is basically the old way of describing what we call a fruitcake now. It was a dessert, and it was really only made because they didn't really know what good desserts could taste like. You know, if you're trying to make a dessert in the days before chocolate was available and white sugar was available, you basically make a bread with a bunch of fruit in it and call that good. So it's basically like a bread with raisins in it. Not my thing, but it was apparently a big, common enough thing that they named this model after it. So the electrons they thought are embedded in this, like the raisins in a plum pudding. So Thomson's student, Rutherford, set out to try and provide more evidence for this. And give this background because it's a really good example of how the scientific method works. Rutherford says, okay, my advisor, the person who's taught me everything I know about doing science research, says that this makes sense, and he's kind of got me convinced too. I'm going to come up with an experiment to try and show that this is what's going to happen, that this is the way atoms are actually built. So this is another case of they didn't really know what they were using, but they had this ability to make these things called alpha particles that had a positive charge. They didn't really know what an alpha particle was, but they knew that certain types of uranium produced these alpha particles. And so they basically said, okay, well, if we fire these alpha particles at a known velocity, when they pass through the plum pudding, with the plum pudding, all this red area is supposed to be positively charged. And positives are pushing away other positives. So basically what comes out the other side should be still the same, but slower. So he set up to do this. He said, okay, I'm going to take a sheet of gold. He chose gold because it's incredibly malleable, which means you can actually just hammer it until it's really, really flat. The Latin word for hammer is mallus, M-A-L-L-U-S. So malleable literally means you're able to hammer it. Gold is very malleable, so you can actually hammer it flat enough. You can make gold foil. It's thin enough you can see through it. It's only a couple of atoms thick. So they said, okay, well, here's what I'm going to do. I'm going to make this gold foil. I'm going to fire these alpha particles at it, and I'm going to measure how fast they're going when they hit it, right before they hit it, and right after they hit it. And what I expect to see, the hypothesis was, there's still going to be alpha particles. They're going to be moving in the same straight line, just a lot slower. Turns out that's not what actually happens. So that guy's name was Rutherford. Like I said, he was Thomson's prize student. He was a student who's like, okay, I'm going to take over Thomson's lab because I'm good at doing research. I'm smart. I'm educated. I'm ready for this. I'm going to prove Thomson's model's correct, and he's going to love me forever for it. What he actually found is that the plum pudding model completely falls apart. When you do this experiment, almost all of the alpha particles go straight through, and they're moving at the same speed they were when they left. Some of them are just barely deflected a little bit, but then some of them bounced off at really unexpected angles. So he basically he took the detector and he turned it into this circular shape so that we could see all the different ways that this happened. So Rutherford, the fact that almost all the alpha particles go straight through. Some of them are deflected in random angles, but they're all going the same speed they were when we first started it. So Rutherford came up with what's called the nuclear theory. Right, and basically he disproved the plum pudding model by doing this, which essentially like burned the bridge between him and his advisor. His advisor, Thomson, was so upset they didn't speak for years after that. Because Thomson was sure that his legacy was going to be the plum pudding model, and his own student proved that it wasn't true. Rutherford didn't want to do that. Rutherford was probably hoping the plum pudding model was true. That would have made his career a lot smoother and been able to maintain those relationships. But good science means you have to report the results even when they don't match with your hypothesis. So Rutherford's nuclear theory that he came up with as a result of this was that almost all of the atomic mass is concentrated in what he called the nucleus. So this nucleus is based on they already knew that a nucleus existed in cells. So he's using the cell as a model for an atom. He said, okay, well, every atom has a nucleus just like a cell has a nucleus. And he said, well, the positive charge must be concentrated in the nucleus. Then all of the positive charge has to be in that little tiny blurb right in the middle. And that's why almost all of our alpha particles move right through it. Because they're not hitting a uniform density, positively charged mass, like the plum pudding model. Mostly, they're just going right by those nuclei. And he said that the nucleus has to be made of a discrete number of protons. Basically, he said, okay, when we have electrons that are negatively charged, there has to, if the electrons only happen in whole numbers, then the protons have to happen only in whole numbers. Because they've got to cancel each other out. And all of the electrons are in this sort of cloud around the nucleus. This is another one of those ones that this works as a theory. And to explain what they saw, but there was always going to need to be some amendments. To this day, this technique is actually still how we determine what the structure of an atom or of a molecule is. We use X-rays now instead of alpha particles, but there's a process called X-ray diffraction, which is basically you shine light on a crystal and you look at which directions the photons bounce. And then you do some trigonometry, some sines and cosines, and some geometry to figure out where the nuclei are based on where things bounce off when you shine light through them. All right, so how does this all come together in the periodic table we know and use today? Turns out there's a couple of key pieces. We've been using the word element kind of the way that they would have in the 1700s. It's a unique thing. It's its own type of matter. We don't really have a definition for it though, until we get to Rutherford and talking about protons, because Rutherford was one of the ones who said, okay, let's define our elements not based on their mass, but based on how many protons they have. What's the overall charge in that nucleus in the middle of the atom? That's going to be our definition for our different types of elements. Different elements have different number of protons. So to go back to the question, well, what happens when we get to the point where we can't cut a copper atom in half anymore? When we cut it in half again, it's no longer copper because you would actually be splitting that nucleus into two. And each of those nuclei is going to have a different number of protons now. So it's no longer copper. This is our official definition of a new element, is an element that has a specific number of protons in the middle. Right, and so that's what this atomic number is. The atomic number is the definition of that element. So in theory, we actually don't really need atomic symbols and names. We just need to know how many protons are in the middle of that nucleus. If I say something has an atomic number of 11, it is sodium by definition. It is Na. So it's a little bit redundant to have both their symbol, to have a symbol and a name to go along with the atomic number. But historically, that's the way we've classified these elements. So we still kind of do it that way on the periodic table. The atomic symbol is the 2-letter abbreviation. Right? The atomic name is just the full written out name of that element. So they all kind of mean the same thing. If I go to the periodic table, that's on the, it'll be on the final. And it opens up eventually. And so boron is symbol is a capital B, and it's always number 5. If you have 5 protons in a nucleus, it is boron by definition. So atomic number 5, the word boron, a capital B as a symbol, all mean the same thing. They all mean this atom has 5 protons in the nucleus. And if you change the number of protons in the nucleus, it's not boron anymore. And so this is actually where this kind of gets us back to the original quest in alchemy, was to find something that to find a way to turn lead, which was a dense, easily available, but worthless metal in the Dark Ages. But it was so dense, it was similar in density to gold. And as we've already established, people and humans throughout history have thought gold was pretty cool. So the original quest of alchemy was to turn lead into gold, which we can now do. What they didn't know at the time was that it's not just different amounts of fundamental elements like fire and water and earth and air. It's actually changing the number of protons in that nucleus. So we're like several layers removed from something that the alchemists would have actually understood without a lot of study, right? Because we had the atomic theory, follow that up with the nuclear theory, follow that up with the research showing that protons are a thing and electrons are a thing. So, and I think I just saw something in my feed the other day. They've actually done this experiment. They weren't actually trying to take lead and turn it to gold. You can't do it in a way that's economically feasible. It takes more energy. You pay more in energy and materials to turn lead into gold than the gold is worth at the end. But we can't actually do that. Turns out particle accelerators are pretty helpful for some of these. But in general, in this class, things don't change what type of element they are. You have to fundamentally change what's in the nucleus for that to happen, and almost nothing does that in natural processes. Yeah.
So since the theory, at least at the time, seemed to be that there's a nucleus that has some number of protons, and from that you can extrapolate what the element is, was it reasonable to assume that helium is 2 hydrogen nuclei fused together and so on to create these other elements?
So that gets to the one of the next slides. Hydrogen's known to have 1 proton. Helium has 2 protons. So do we just stick the two protons together? It turns out that is basically what's happening. But because those two nuclei, if we said we had a hydrogen nucleus with one proton, the helium or another hydrogen that's a single proton, if we can slam these together hard enough, in theory, we could make a helium. The problem is that both of those nuclei are positively charged. And what do positives do to other positives? Push them away, right? So we basically need to overcome that force that's pushing things away. We have to slam them together so hard that we get past that repulsive layer. It turns out that's not easy to do. So that's why we use particle accelerators, and so that would be a fusion reaction in terms of nuclear reactions. The way we set up fusion reactions in bombs, we actually use regular atomic bombs to drive two chunks of, I think they use lithium and hydrogen and some neutrons. But basically you need atomic bombs as the fuel to slam these things together hard enough to actually cause a fusion reaction. So it's not an easy thing to do in nature. But the other issue is that if you were able to do that, if you actually look at what the naturally occurring helium on Earth, its mass number is actually 4 times greater than hydrogen, not just double. So they basically said, well, that extra mass seems to only happen in whole numbers as well. We only got whole integer values relative to each other when we looked at these individual atoms. And so they said, okay, well, that extra mass, it's got to be neutral because it's not affecting the charge. And it has to exist because we can measure the difference in mass between hydrogen and helium. So we don't know why they're there, but there's this other stuff called neutrons that has to be in the nucleus as well. All right, so now we actually have 4 things on our periodic table. We have the atomic symbol, the element name, and the atomic number, which always will go together. Right? If it's argon, it's 18 protons, full stop. And AR is basically just the abbreviation for argon. This other piece, though, has both the atomic number and some of those neutrons associated with it. The mass number of an atom is basically, it's going to be really close to a whole number. And it's going to look like the number of protons plus the number of neutrons. So we know this is argon. We know that argon, by definition, has 18 protons. The rest of its mass is neutrons. So the way we would write this more detailed, this is what it looks like on the periodic table. If we were talking about this specific atom, we'd say it's an argon with a mass of 40. So you put it up and to the left of the symbol, or we could write it as argon 40. So argon 40 is talking about a specific atom that has 18 protons because it's argon, and the total mass adds up to 40. Well, if every proton has a mass of 1, remember Avogadro, and he said, okay, we'll call hydrogen nucleus, we'll call that 1. How many neutrons does it have to have? They have to add up to 40, right? So 40, our mass number, minus 18, which is our number of protons, which we abbreviate as a lowercase p with a positive charge. So our total mass is 40. We have 18 protons. Means that we must have 22 neutrons, which the abbreviation is a lowercase n. Sorry, that's wrong. With a 1. And actually, Sorry, like that. So. Up and to the left. Mass number. Whatever is up and to the right is where you would write the charge. How do we figure out the charge? What causes the charge?
The difference between neutrons and protons and electrons.
Right, so are neutrons gonna affect the charge at all? Neutrons are called neutrons because they're neutral. They don't have a charge. So our mass is always gonna be based on our neutrons plus our protons. But our electrons are tiny. Our electrons were so small in terms of mass that we could basically say they have zero mass within sig figs. They're 2,000 times smaller than a proton. Neutrons and protons are close to the same size. But electrons are 2,000 times smaller than both of them. So they basically, that mass is not affected by electrons. So what is affected by electrons? If we change the number of protons, what do we change about an atom? We're gonna change its charge, but we're also gonna change what element it is, right? Once we know it's a specific element, if we change how many electrons we have, that's gonna change the charge also, right? So let's say we had sodium. It's got an atomic number of 11. So how many protons does it have? 11. How many electrons does it have if it has a charge of 0? If it's got a charge of 0, if it's neutral, it's got to have the same number of protons and electrons. So if it has 11 protons and it's neutral, it also has to have electrons. We abbreviate electrons lowercase e with a negative charge. So just like protons with lowercase p with a positive charge, electrons is e with a negative charge. So we can, if we change the number of protons, we change what element it is. We change the number of electrons, we change its charge. If we lose an electron from a sodium, if we had 11 protons, but only 10 electrons, what's the overall charge? We have a mismatch of 1 here, right? Which means our charge is going to be 1. Is it going to be positive 1 or negative 1? We have 1 extra proton, so that gives us a +1 charge. So sodium with a +1 charge, that tells us, the fact that it's sodium tells us it's 11 protons. The fact that it's got a +1 and it's sodium is, we work backwards to get, it must have 10 electrons.
So the reason that the atomic weight got a whole number because the electron's weight may change between different charges.
There's a few reasons. Most of these are pretty close to whole numbers if you look at the mass number, right? But some of them aren't. Fluorine's got a mass number of 35.45. That's not really close to either direction, right? So changing the number of neutrons doesn't change the charge, doesn't change what element it is, it changes the mass. So for instance, we'll use chlorine since I just brought it up. Chlorine has a mass of, chlorine is number 17. So it's got 17 protons. But it's got a mass of 35, usually. But it turns out if you change the mass number, but you keep the number of protons the same, it's still chlorine. You didn't change the charge. You just changed how much that nucleus weighs, so it's still chlorine. It behaves the same way as chlorine. It's changing the mass number. Just changes what isotope it is. So what's on the periodic table is the average of what we find on Earth. If you pick a chlorine atom at random on Earth, there's a 75% chance it's chlorine 35, but there's a 25% chance it's chlorine 37. Roughly. Right, so these are the two naturally occurring isotopes of chlorine on Earth. And so, to recap, changing number of protons changes what element it is. Changing the number of electrons doesn't change the element, it changes the charge. And changing the number of neutrons changes the mass, but not the charge, and doesn't change what element it is. Right? Those are our three fundamental subatomic particles that we'll deal with in this class. Protons, neutrons, and electrons. The other thing I keep meaning to go back and reiterate this. All letters, all atomic symbols have the first letter capitalized. That's it. This is another case. This is why we start by paying attention to our capitalization on our units, because it matters for our elements as well. Good example. Let's see, what's a good example? SC. So for instance, if I wrote SC, that's scandium. Capital S, lowercase c. If I write SC, that's a sulfur attached to a carbon. So we have to be careful with our capitalization. You might need to change your handwriting a little bit when you're writing these atomic symbols. Because the other thing you can't do that. Is that a carbon and iodine, or is that a chlorine? You have to make sure it's explicit when you write this. If I wanted carbon and iodine, I would write it like this. If I mean it's a chlorine, I write it like that. You have to be, or you would write it like that. But you have to be really, really clear that your capitals are capitals and your lowercase are lowercase. Right? Otherwise, things are getting really confusing. All right, last announcement. This is going to be one of the few times I tell you, you just have to memorize something. And this is the only time I'm going to tell you that I'm going to take away your periodic table. Next Wednesday, so not 2 days from now, but a week and 2 days from now, you're going to have a quiz on the periodic table. Just on the names and the symbols. I'm not going to give you a periodic table. It's just going to be, if I write this C, you have to write scandium. If I write C, you have to write carbon. No numbers. You don't have to know where it is on the periodic table. You just have to be able to say symbol to name and name to symbol. Right? And all 118 are fair game. Flashcards, you already know most of them, and you've got a week to prep. Flashcards, it's gonna focus on the top half of the periodic table, but everything's fair game. More details on Wednesday. I'll see half of you in an hour.
What?